I believe in the last class, so we just started discussing about uh, eigenvalue problem. So we are looking for the principal stresses, and we showed that that eventually boils down to an eigenvalue problem that actually is an optimization problem where we would try to optimize. And I'm just saying optimize and not mentioning whether am I trying to maximize or minimize this. So trying to do that because I'll be doing both, maximizing, minimizing, and everything. So it just turns out to be an optimization problem involving a Lagrange multiplier because there is a constraint, and this is what I'm actually trying to optimize. Okay, and that eventually got us over here. Okay, and arriving at this equation, we used the idea that the stress matrix is a symmetric tensor. Okay. Uh, So we are supposed to now solve this equation to get the corresponding values of nx, ny, and nz. So this n vector is nx, ny, and nz. But if you notice carefully, this is a set of homogeneous equations. The point being that this the right hand side is composed of three zeros. Okay. Uh, so so that basically means so so are you clear with up to this part?
Yes, sir.
Okay. So now you have three equations. Okay, and all are homogeneous equations. Okay. So that is, there are two possibilities that uh, mm, that three of them are inconsistent. Okay, so to give you an example, for example, 5x minus 6y plus 3z equals 0. That is one equation. Okay, then say 2x minus 3y plus z equals 0. Okay, now two equations with involving three variables. If there are two equations, two homogeneous equations, that is fine. But the third equation cannot have the constant term, okay, or the numeric term cannot be zero. Okay, I mean, if it is zero, then there are two possibilities. One possibility is that let's say um, 3x minus 4y plus 2z equals 0, which means this is inconsistent. Okay, if you look carefully, if I subtract from equation 1, if I subtract equation 2 from equation 1, okay, I would be having 3x minus 3y plus 2z. Okay, but instead I chose to do 4y, but that cannot be true. Okay, it's either that, because if I take 3x minus 4y plus 2z, that makes this equation linearly independent of the other two. It means the coefficient 3, 4, and 2 cannot be composed by uh, mm, uh, linearly simply subtracting the first set of coefficients, that is 5, 6, and minus 3, and 2, 3, and 1. Okay. So the coefficients become either linearly independent, which means either the rank of this matrix. So this itself is a matrix, right? It's a symmetric tensor. Okay, sigma minus lambda I. Either that matrix is you know the rows are linearly independent, or in other words, that either that has a rank of 3. Okay. Or that is it is a non-singular matrix. There are various ways to describe that. Or also that sigma minus lambda I, the determinant of this matrix, okay, is not equal 0. Either that is true, okay, then this sort of situation arises with three homogeneous equation, that the third equation is inconsistent with the first two. Okay, it's either that situation, or it is a situation something like this, where the third equation is a linear combination of the other two. That way the system of equations are consistent. You see, we are stuck in the second case. And how do I know that? Because this set of equations have only two independent equation. Okay, that is linearly independent uh, equations, two independent equations, and the third equation is actually dependent. And what serves as the third equation is the constraint equation, because that's the equation that you get when you take gradient of pi with respect to lambda equals 0. That implies, so now you have four unknowns. So this actually, please remember something like where how you found out reaction forces. So the three equations that you see here are supposed to give you not just nx, ny, and nz, but it is also supposed to give you lambda. Okay. But then there would be four equations, four unknowns, and three equations is not sufficient. So this is your fourth equation. Okay, so your nx, ny, and nz are supposed to mm, satisfy this constraint, and after that they can appear in this equation, and that way you get to calculate lambda as well. Okay, so together the four equations are uh, so together you can use this set of equations. So this situation also happens when you try to solve infinite element method with a a constraint at one of the ends. So there you cannot simply find out the system matrix is not linearly independent. Okay, and instead you are supposed to find out the reaction force out of it. So the three unknowns are not the three deflections there. If you had 3 degrees of freedom, because one of them would be known to you at least. And then you are trying to find out the reaction force corresponding to that deflection. To be frank, that reaction force that we talk about, that reaction force is essentially equivalent of Lagrange multiplier. Okay. So this is what we have in reference to this situation. We have two independent equations, and the third equation is this one. So that's why the rank of this matrix is you see, to get the rank of this matrix you need to have the magnitude of lambda. So that also is not known to you. So together the four equations are linearly independent, but once you know the value of lambda, these three equations are not linearly independent. Okay, so the only possibility that we can allow is to be a singular matrix, or to have a matrix with three rows, not linearly independent or linearly dependent, whereas we cannot allow an inconsistent system of equations, because that way the solution would be impossible. So we are allowing that, which basically means the rank of this matrix is 0, which also means that determinant of this matrix equals 0. Okay. And if you you know that if you write down this, if you write this down, so you get the characteristic equation, which basically tells you that lambda cube minus I1 times lambda squared plus I2 times lambda minus I3 becomes your cubic equation from which you are supposed to solve for lambda. Okay. So that is actually, although I'm just showing it for a symmetric matrix, that actually is general. Okay, and true for whether you have a symmetric or a skew symmetric or a mixed tensor. So any general tensor T can be divided into a unique symmetric and a skew symmetric part. The symmetric part, of course, is T plus T transpose divided by T transpose. Oh, T transpose divided by 2, and W, of course, is T minus T transpose divided by 2. You can check, if I take transpose of W, that would be T transpose minus T, which is the negative of T minus T transpose. Okay, and if you add these two, you are going to get T plus T divided by 2, which is T. Okay, so this is the unique representation. Okay, and for any general tensor, this is actually true, not just a symmetric tensor. But then again, let's not go into the details of how you get, actually this is how you know you are going to get the eigenvalues. But what do we have to think about those eigenvalues is that the Tn, the normal component of traction that we talked about, which was indeed n times sigma n. Okay, so these n's are actually your eigenvectors. Okay, in reference to general eigenvalue problem, but in reference to principal stresses, these are called principal directions. Okay, so this quantity essentially becomes lambda times n dot m. Okay, now you see this is a cubic equation, so you get lambda equals lambda 1, lambda 2, lambda 3, three roots, right? So what you see from here is your normal traction. Okay, that is the quantity that you are originally trying to optimize, this quantity, right? So that essentially on once you choose a principal direction, once you choose a cutting plane normal to a principal direction. Okay, so there uh, the the Tn value is actually the Lagrange multiplier, because n dot n or n transpose n is actually unity, right? N dot n, because n is the unit normal. You see, so this Tn, the principal stress that we are, or the the optimum normal traction that we are talking about, that is actually your uh, the eigenvalue itself. Okay, and now let's see how much is your shear component. So is it clear up to this part? Can I delete? Okay, I'll not delete. I'll just keep on doing here. So, but is up to this part clear to everyone?
স্যার ওই এনটা কোন সময় প্রিন্সিপাল ডিরেকশন হবে?
When it is the solution to this optimization problem. You see, principal directions are those directions that if you take a plane normal to that direction, that you get to optimize Tn. It can be maximizing, it can be minimizing, but it is optimizing. Okay, the normal component of traction will be maximized. So when once you are done solving this, and once you get this eigenvalue problem, okay, this the n that you get, and so this equation, so this three equations, and this is a single scalar equation. So together four equations. Once you solve these four equations, you get to calculate the lambda value, and you get to calculate the n value, right? Lambda, of course, comes from this equation, and once you substitute that, you get once you substitute this over here, so you have two independent equations from here, and this equation serves as a third equation. So with the help of that, you get to calculate the three components nx, ny, and nz. Okay, and that solution, okay, so that normal actually is on that plane on which the traction value, the normal component of the traction value, is maximum, right? Or minimum. Okay, it is optimum. That's what I'm trying to say here. So when it is a solution of this eigenvalue problem, so that's when it is the principal direction. Okay, and why I said directions, because there are three eigenvalues, and depending on the eigenvalue, there would be three different eigenvectors. in general there would be three different eigenvectors. So these are principal directions. Those are the directions in which your I mean, if you take a plane normal to that direction, that you get the optimum traction. Is it clear now?
Yes, sir.
Okay. Acha. Now let's try to do this. Okay. Let's try to find out on on. So this plane we would call as principal plane, and there are three principal planes. So on principal plane, if I calculate the magnitude of the traction, or this, the magnitude of the square of the magnitude of it, so that essentially is as you can see, sigma times n is the traction, right? Dot sigma times n, which basically is lambda times n, because it's a principal direction, dot lambda times n. Okay, and that essentially gives us lambda squared times n dot n, which basically says lambda squared, because this part is unity. Okay, now the shear component of the traction is essentially the magnitude of the traction minus the normal component. You see, imagine this is the plane at which you are cutting the geometry. This is the normal. Then let's say this is the traction. Okay, so it has two components. This part is your shear component, and this part is your normal component. And our whole job in this optimization problem was to get the maximum or minimum normal component. And as it turns out, once you on a principal plane which optimizes the Tn either in a maximum form or a minimum form. Okay, and actually, uh, um, mm, so this eigenvalue of yours is actually the optimum value of Tn, right? So it is not just maximum or minimum. We'll come to that in a minute. But you see, so Hmm. So the traction has two components, shear and the normal. Now, once you are on a principal plane which optimizes Tn, it could be making it maximum or a minimum. Okay, but as it turns out, on a principal plane, the Ts component would be how much?
0.
Zero. So on a principal plane, there is no shear traction. We are used to calling it shear stress, but it's not actually shear stress, it's actually traction, because stress has more components than a normal and a shear component. Okay, the traction has three components, Tx, Ty, and Tz, or it could be represented with reference to a given plane. Okay, the traction could be represented as a normal component and a shear component. The shear, of course, can be represented in you know two orthogonal directions, on two orthogonal in plane directions. So one is the normal direction and two orthogonal in plane direction. So the traction itself can be represented with the help of these three orthogonal directions. Okay, now of course one part of is normal, the other part, the combination of the two in plane directions is actually shear. Now that combination of two in plane direction, which is the shear, it turns out to be zero on a principal plane. So on a principal plane, now this statement is very important. On a principal plane, the traction can simply be represented with a single number, and that number is your eigenvalue, or also known as your principal stress. Let's say uh, this is your lambda one. Okay, that means this is the first eigenvalue that you have taken. Okay, and then those normals should also be represented as the first principal directions. And once you take those first principal directions, then you get sigma one. Okay, which is actually equal to lambda one. So sigma one is your first principal stress, which represents the total situation of traction on a principal plane. Okay, so there is nothing else except for the normal value. Okay. So there is a principal stress. Okay, and there are three of them: sigma 1, sigma 2, and sigma 3. So this is the highest one, sigma 1, the signed value. Okay, let's say it is plus 50, and let's say sigma 3 is minus 100, but still smaller than sigma 1. We're not comparing the absolute value, we are comparing the signed values. And sigma 2 is actually the middle value. And actually, if you think about it, if I were to represent the normal, okay, kind of with an angle, with the horizontal, okay, and that is only possible if we are doing it you see, with the planar normals. Okay, uh, so if I change theta, okay, we have three situations. One is, so this is how the normal component of the traction changes, and let's say it is minimum somewhere, then it's a saddle, and then it becomes a maximum. This saddle portion is actually your sigma 2, and this one is your sigma 3, and this one is your sigma 1. Okay, uh, so that's the idea. But the actual situation is, out of nx, ny, and nz, the two components would be independent. Okay, so when you are talking about three-dimensional normals, not planar normals, then you have two independent components. The third component is, of course, is a result of this one. So by varying those two independent components, you can have an array of value of this Tn, and in that is, at certain values, is your principal stress, or Tn is a minimum, somewhere it is a saddle, and then somewhere it is a maximum. Okay, so now we have learned that there are three eigenvalues, three principal stresses, and three principal directions or eigenvectors. Okay, so n1, n2, and n3. Uh, but we do not know whether n1, n2, and n3 are normal to one another. That means they are, of course, mm, the unit normals. Okay, but we do not know whether they are orthogonal. Is it clear up to this part?
Yes, sir.
Okay. Now, this symbol IFF means if and only if. Okay, for any symmetric tensor, okay, it can be shown that its eigenvectors can always form an orthonormal basis. Okay, there is a basis of this type: n1, n2, and n3. And for this part, I would suggest you can check the book on continuum mechanics. Actually, you are supposed to look at a book on linear algebra, but this is where I am certain that you will definitely find it, by Chandrasekhar Joe. There, this proof has been shown. Okay, and try to go through that proof. Okay, and that way you will understand why this is true. Now look at the statement: n1, n2, and n3 can form. Okay, that does not mean that they would necessarily form, but that they can be chosen in a way. That means there are multiple solutions in some situations, okay, where they can be taken in a way that they are orthonormal basis. Okay. Now there are, if you are dealing with symmetric tensor, there are three possibilities. One is lambda 1 not equal to lambda 2, not equals lambda 3, not equals lambda 1. Okay. The second situation is lambda 1 equals not equals lambda 2, which equals lambda 3. And by that, it means that lambda 3 is also not equal to lambda 1. And the third situation is lambda 1 equals lambda 2 equals lambda 3. Okay. Now, when all the three eigenvalues are same, say, then your symmetric tensor is essentially this quantity. Okay. And that is how it looks in any coordinate system. Okay. Also, this means that I can take a random vector, let's say E1, random unit vector E1. And if I multiply I with E1, sigma with E1, okay, then I'm going to get lambda star times E1, okay, which basically means for any arbitrary unit vector, any arbitrary unit vector serves as an eigenvector for a symmetric tensor of this nature, whose eigenvalues are all same. You see, in order to have this situation, the characteristic equation must be lambda 1 minus lambda star, lambda 1 minus lambda star. It's a cubic equation, right? Lambda 1 minus lambda star. The only way that is possible is if the symmetric tensor is something like this. So that means any arbitrary vector, okay, is an eigenvector to this symmetric tensor, which means that I can choose a set of orthonormal vectors, let's say E1, E2, E3, and make them as my three eigenvectors. Okay. So I can form an orthonormal basis out of it. Okay. Now the second situation where two eigenvalues are same and one is different. So this is the situation that we have. We have one eigenvector, okay, which is unique. Now then there is a plane perpendicular to that eigenvector on which lies, it can be shown actually, and for that you need to look at this reference, on which any vector is an eigenvector, any unit vector is an eigenvector to the symmetric tensor. And because any vector is an eigenvector, I can choose two orthogonal vectors on that plane, okay, and thereby making each of the vectors, each of the eigenvectors, okay, orthogonal to one another, okay. And therefore again I can form an orthonormal basis out of this system. For the third situation, actually you get unique n1, n2, and n3, okay. uh, this is, and you know and they are again orthogonal to themselves. So there is just one solution. Here there may be multiple solution. Here, of course, is also infinite solution in these two cases. But in the first situation, you have a unique representation. And this is how the proof works. I'm considering case 1 where none of the eigenvalues are same. Now, n1 dot sigma, sigma times n2, as we had discussed in one of our early classes in finite element method, can be shown as n2 dot sigma transpose n1. Okay, but then again, stress is a symmetric tensor, so I can drop this quantity, which basically means this quantity is same as this quantity, and also this quantity is same as this quantity. Now, since lambda 1 and lambda 2 are not same, the only way these two quantities are same if this equals 0, which means if I take, arbitrarily any two eigenvectors, okay, they are going to be orthogonal. Is this part clear?
Yes, sir.
Okay. And actually, three eigenvalues being different from one another is the general case. And if you can show this proof, the others also work. The point is that even if they are really same, I can think of that this thing is lambda 2 is, let's say, अच्छा, lambda 2 is, let's say, lambda star minus 10 to the power minus 20, and lambda 3 is lambda star plus 10 to the power minus 20, which basically means that that lambda 1, lambda 2, and lambda 3 are not same. If I just imagine in a situation where there is an infinitesimal difference between lambda 2 and lambda 3, there also you are going to get, you see, orthonormal basis. Okay, that also implies that when in the limit this goes to 0, you are going to get an orthonormal basis. May not be unique, but you still get one. Okay. Acha. Now, you have seen two meaning of the orthogonal matrix. One is that it can rotate a vector, okay, or it can rotate a matrix, okay, and it can also change the representation from one coordinate system to other coordinate system. Okay, and this time you will see what Q is composed of. Now, if I choose, or if I get n1, n2, and n3, which I can always get as an orthonormal basis, actually I should be calling it orthonormal base. Once I have each of the basis vectors, then I have orthonormal base. So all of these vectors are normal to one another. Okay, and in any situation I can always get three orthonormal vectors, eigenvectors or principal directions. So once I have the orthonormal base, then I can write, let's say, let's call a matrix A, which is formed by, so each row is formed by the eigenvectors. Okay. Now, if I multiply A with A transpose, so what am I supposed to get? Can you do this calculation? Can you tell me what am I going to get? What are the components of the matrix A transpose? What is the first term? N1 dot N1, right?
Yes, sir. N1 dot N1 will
How much is that? First term is this row and this column, right? So N1 dot N1 dot product. Each term in this row multiplying each term in this column. So what is the dot product? N1 dot N1. How much is N1 dot N1?
1
1. Acha. Now let's move on to the next term. So N1 dot N2, how much would be the value?
0 স্যার ইউনিট ভেক্টর হবে
So it would be a unit vector. So A is such a matrix, when multiplied with A transpose, it gives you an identity matrix. Okay. Then what sort of matrix A is? A then belongs to orth orthogonal tensors, set of orthogonal tensors. And if you do take N1, N2, and N3 as a right-handed system, if you take N1, N2, and N3 as a right-handed system like this one, you understand what is a right-handed system. So then this is actually a true rotation tensor or orthogonal tensor, which basically means it's just like Q. Okay. Now, if I do this, if I if I multiply sigma with A transpose, okay, so that is like this quantity. Okay, so as if I'm multiplying each column individually. That's what it is, right? So what would be sigma times n1? What is sigma times n1?
স্যার এন এন ডিরেকশনে যে সিগমার কম্পোনেন্টটা হবে সেই কম্পোনেন্টটা
No, this is what we have been discussing for last 1.5 class. N1, N2, and N3 are principal directions of sigma. That basically means this is lambda 1 times n1. Or since we are now representing them as principal stresses, it is sigma 1 n1. Okay. Now if I multiply A with sigma A transpose, then what we would be getting? Again, I'm this quantity would be simply, please understand, sigma 1, sigma 2, and sigma 3 are simply scalars, the eigenvalues. So if I do this product, instead of an identity matrix, I would get a diagonal matrix with three principal stresses. Is it clear to you?
Yes, sir.
Okay. Now let us do a simple derivation to understand what doing A sigma A transpose means. Imagine this is our xy coordinate system, and this is x prime y prime coordinate system. And let's say the angle between the two is phi. Okay. So therefore, I can represent I prime. I hope you understand what I mean by I, as cos phi times I plus sine phi times j. Similarly, j prime is minus sine phi I plus cos phi j. Okay. So now if I write A equals cos phi sine phi minus sine phi cos phi. Okay. Let's see what it does. Now imagine this is a vector v which makes an angle of theta with the x prime axis. Okay. So v can be represented as v cos theta, or v can be represented as, in x prime y prime coordinate system, v cos theta, v sin theta, where the scalar v is simply the magnitude. Now when it comes to v representing in xy coordinate system, that is v cos theta plus phi, and v sin theta plus phi. Okay. And then multiplying A with the representation of V in xy coordinate system. Okay. would give us v times cos theta plus phi times cos phi, then sine phi plus sine, no, not, yeah, plus sine phi sine theta plus phi. And again, minus sine phi, this row and this column, sine phi cos theta plus phi plus sine theta plus phi cos phi, which basically means cos of theta plus phi minus phi, which is cos phi, and sine of theta plus phi minus phi, which is sine of phi, which is basically v represented in x prime y prime coordinate system. So once you take this basis vectors or eigenvectors or principal directions, of course these principal directions are represented in global Cartesian coordinate system. So if you make a diagonal tensor, an orthogonal tensor with all the principal directions uh, uh, represented in the global Cartesian coordinate system, that is, the global XY coordinate system. Okay, and then you multiply that to a vector, you get multiply that to a vector in the global Cartesian representation, you get the vector in that principal basis, that is the n1, n2, n3 basis. Okay. Similarly, if you multiply A sigma A transpose, now this sigma over here is in Cartesian representation, global Cartesian representation, global XY coordinate system. So once you multiply A sigma A transpose, you are actually going to get the representation of sigma in the principal directions or the basis direction. Okay. So this representation right here shows how you would see the stress tensor if you were to look at the stress tensor from the principal base, which is n1, n2, n3. Let's say it is something like this, not of course aligned with the global Cartesian. Okay, so let's say this is the global Cartesian. Okay, so you actually get the representation of the stress tensor. That's what it means. This diagonalization has some meaning, and that meaning is you get to represent your stress tensor in the principal base. Is it clear up to this part?
Yes, sir.
Yes, sir.
Okay. Now begins the fun. If I were to represent the stress tensor in the global Cartesian, this is the effort I must put. If I select a given plane, there are three directions of tractions. Okay, and those three only make a single row or single column. Okay, of a you see of the stress tensor. So this one is, let's say, if this direction is x, this direction is y, and this direction is z. So this one is of course sigma xx. Then this one is sigma on that is acting in y direction, but on a plane normal to x-axis. This again is sigma zx. Okay. So unless I use three planes and on each plane I show three directions, the number of components of stress is not complete. Of course, we can utilize that the fact that the stress is a symmetric tensor, which means I can call it sigma xy. Okay, and the other component also sigma xy. That is fine. Okay. But I need to use 9 arrows to represent the stress tensor, and I need to use this cube right here to get the 3 planes on which am I supposed to represent the stress tensor. With principal directions, it is this simple. Okay, on the principal direction, you know that on a plane normal to n1, the traction is simply normal to the plane. Same here. Okay, so I only need 3 arrows. And although the stress tensor is and always will be a matrix, a second order tensor, but in the principal plane or principal coordinates, I get to represent that as some vector. Because you see, in the global Cartesian representation, I need to specify a given plane. Then on that given plane, I need to specify 3 directions. Here, once I specify a plane, there is only one direction. Okay. And instead of representing sigma like this, sigma 1, sigma 2, sigma 3, okay, I get to represent that as sigma 1, sigma 2, sigma 3, but only in principal directions. Okay. So the tensor for me becomes a vector. Is this part clear?
Yes, sir.
Okay. One more thing. If a matrix in any coordinate system looks like this, okay, so what is the trace of this coordinate, this matrix? What is the trace of sigma?
Sigma 1 plus sigma 2 plus sigma 3.
Okay. Now, this we know is the I1, and I1 survives any form of coordinate transformation. So going from global Cartesian to your you see your principal directions. Okay, the I1 will still remain the same, right? That's why it's an invariant. We showed that trace of I mean, all I'm trying to say here is A transpose is trace of A, right? And we said that is true for I2 and I3. Now, how much is the value of I3 then? Right?
Yes, sir.
Okay. What about I2? I2?
Sig-
Right?
yes, sir.
From this, from this representation, can you find out? You see, there are 3 equations and 3 unknowns, right? 3 equations and 3 unknowns. Then you should be able to figure out the 3 unknowns, right? So can you try to? I mean, they are not all simultaneous linear equations. They are non-linear equations. But can you use them to find out a solution? So, for example, you can take sigma 2 plus sigma 3 equals, or for that matter, you can take from the first one, you can take sigma 1 equals I1 minus sigma 2 minus sigma 3. Okay. Then that also equals I3 by sigma 2 by sigma 3. Or actually, you see, you can substitute that over here in the third equation. So there you can say that it is I1 minus sigma 2 minus sigma 3 multiplying sigma 2 plus sigma 3 plus sigma 2 sigma 3. Okay. So I1, okay, and then sigma 2 sigma 3 is I3 by sigma 1, which is I1 minus sigma 2 minus sigma 3. Okay. So substitute that over here and try to see what sort of equation do you get. Try to get a solution out of it. ওকে, এটা কি পারলে তোমরা করতে?
স্যার সবে সিগমা ওয়ান দিয়ে একটা ইকুয়েশন আসছে।
Actually, it would be kind of other way around. You see, the solution is that whether you take sigma 1, sigma 2, or sigma 3 by the substituting for others. Okay, so in the end you are going to get an equation like this, which is the characteristic equation. um, like okay, now if the solutions of this equation are sigma 1, sigma 2, and sigma 3, so this is how it should work, right? Okay, so it is lambda squared minus sigma 1 plus sigma 2 times lambda plus sigma 1 sigma 2, and then lambda minus sigma 3 equals 0, which is okay. So this is another way of proving that your the invariants are going to be same even in the principal directions. So I1 is essentially then comparing the terms, the coefficients of the like powers on either side. We can say that an I3 equals sigma 1, sigma 2, sigma 3, and so on. Okay, so it is easier to prove that in the reverse. Actually, majority of what we have been discussing since the last class, you'd probably find that majority of it in you see in your textbook, which is Theory of Plasticity by J. Chakraborty. So in that you will find majority of it. Some of it you might not find. Uh, and that is because in that book also, there are a lot of steps that has been skipped. Now I'm just trying to do it as much elaborate and as much understandable as possible. Okay, because these are the, like in finite element method we did, these are the beginning set of classes, and there we go, in the extreme detail, in the extreme elaboration and explanation, so that uh, our understanding is built up. Once that is done, then we can move faster. And at this point you might not understand what is its any form of connection with theory of plasticity. But the problem is, uh, in our curriculum, okay, there is no separate course where we can discuss this. And without discussing any of this, okay, I mean, even in theory of elasticity, that beyond a certain point you cannot simply work with scalar equations. You need to go with matrices, and think about that in reference to plasticity. Okay, so there it becomes really difficult. Okay, uh, but I just want to know, in the last semester's theory of elasticity course, did you cover any of this: principal directions, principal basis, principal stresses? I believe some of it must be covered.
Yes, sir.
Yes, sir.
So all of this you are familiar. So I'm just doing this stuff mostly redundant.
Yes, sir. These proofs were done, but in some other methods.
Okay, okay, but do you understand all of this? It may be some other method, but do you understand all of this?
Yes, sir.
Okay, okay. But if I
Sir,
ask you, let's say, yes,
sir, the models you have discussed in the first day, I couldn't find that on in Jane Chakraborty book.
model as in, okay,
Plasticity models.
as in your block stream models. No, those are not
Yes,
there
sir.
in Jane Chakraborty's book. Okay, uh, that I don't think I mentioned that would be in the textbook. That's actually not in the textbook. So, but I showed you one paper, right? Okay, actually it's not a paper; it's a book chapter. So you'll find it over there. Not only that, you would find countless references over the internet where block string model has proved to be useful. Okay, so for that you need to, the search in the internet.
Okay, sir.
Okay. Achha, even if we are doing something that has already been covered in your curriculum, let's just for the time being stick to it. Um, Now these are the directions of maximum normal component of the traction or minimum normal component of the traction. Okay. What about the maximum shear directions? Did you do anything with the planes that have the maximum shear? Did you do that derivation in theory of elasticity?
No, sir.
No. I guess that's because shearing is more important for plasticity than in elasticity. Uh, because shear is the only way the plasticity does happen. Uh, I mean, the metal plasticity, right? So on theory, of course. Okay, so all of those disclaimers must be there. So, other than metal plasticity, what other sort of plasticity is there? There is soil plasticity. Okay, and in soil plasticity, there is certain dependence on the non-shear part of the stress, and I'll explain as we progress We'll go slow in the first few classes, and I'll explain how we need to understand the different components of stresses. And I'm not just talking about the Cartesian components, which are basically 9 components, 6 independent, but as in hydrostatic and the deviatoric part. Do you understand what is a hydrostatic stress and a deviatoric stress?
Yes, sir.
Oh, you do? Okay, which is great. But we need to go
Hydrostatic
in
method.
detail. Hydrostatic you understand, deviatoric you don't.
No.
If you don't understand deviatoric, then there is no point of understanding hydrostatic. You don't understand hydrostatic stress. Okay, so there is one way to look at that. Okay, so yeah, then other components we'd talk about, but let's first talk about the directions of maximum shear. Now, this maximum or minimum are in reference to both referenced as maximum. The sign would just be inverse. Okay, but then that is the direction of shear, right? So the point is, uh, mm, when we talk about the directions of maximum shear or the planes of maximum shear, essentially what we are not talking about where the shear is minimum. By minimum here, of course, we mean that zero shear stresses, that is the principal directions. Okay, acha. So let's pose our optimization problem. So we are now trying to optimize this quantity right here, maximums, with respect to what? N, the three components of N. Of course, the three components are not independent; they are subject to a constraint. That's why you later bring on a Lagrange multiplier. But let's save that for later. So here we are trying to optimize this quantity. Okay. So we are actually trying to optimize the shear component of this traction, which is the total minus the normal component of the traction. Now, n again here is an arbitrary normal to an arbitrary, sorry, it's a normal to an arbitrary plane. It's not a principal directions right now. Okay, so t squared minus tn squared. Now, t squared is sigma n dot sigma n, and this of course is n dot sigma n squared. This is a scalar, right? N dot sigma n is a scalar. So I need to simply make a square of that. Uh, if I write initially, this says uh, summation over I, summation over j, sigma ij in j, and then another summation over k, sigma I k in k. Okay, because I'm just multiplying the ith terms of each vector, and this component right here is going to be summation over I, summation over j, sigma ij in I in j. Okay, and then this thing squared. Okay, of course this is not how you represent in initial notation. In initial notation I should be doing another set of this operation. Okay, but which basically means I should be doing this. You see here there are two dummy indices j and k. Here there are two dummy indices I and j, only to represent what's being squared. Now, when being squared, it should also be represented as sigma KL NK NL. But let's not go there. Let's simply, in either case, you're going to get the same result. We are simply going to square this one. Okay. Now, this, of course, is subject to, and that needs to be supported with this Lagrange multiplier. So we now want to maximize this quantity. So whatever we had written for pi plus lambda times 1 minus n transpose n. Okay. So so this derivation we will do in the next class. Okay. So it is already there in your textbook. If you want to go through it, go through it. Okay. That probably has been done in a different way. Okay. So just go through it, and then we would discuss in the next class. Okay.
Okay, sir.
Okay, sir.
Okay. See you on Wednesday.
Okay, sir.